Hello and welcome. We're going to start chapter 5 now in this book by Carroll and Ostlie. And in chapter 5, we're going to be talking about the interaction of light and matter. The game plan is to look at a few slides and do a demo for section 5.1 on spectral lines, say a few words about 5.2 on photons, and then we'll go to the whiteboard behind me to say some more about section 5.3, the Bohr model of the atom. But let's get into the PowerPoint slides to start this out. We see on the left, we have a light source that's shining through a slit, and then that light continues on to a prism. And as the light enters and leaves the prism, light of different wavelengths refracts, bends different amounts. Newton first realized this, that white light was made up of all the colors of the rainbow. And you see that here. Where does bad light end up? Of course, bad light ends up in prism. Yes, very funny. So now in section 5.1, we're talking about spectral lines. Just like that prism we were seeing a moment ago can break up light into its constituent wavelengths, a diffraction grating can as well. And I have a demonstration where I've used a diffraction grating to show you that I recorded previously for another course. So I'm going to insert that right here, and then we're going to come back to this slide and keep on going. Diffraction gratings, I've got a few of them here. They just look like little slides or sheets of plastic, and they have many, many little slits etched into them. Right? So this one has 1,000 lines per every millimeter. Wow. You also sometimes, wear these diffraction gratings. So as glasses for fun. I'm going to show you here what kinds of things the diffraction grating does. As you send light through a diffraction grating, it will behave similarly to what happens when you send it through a prism like this. The different light wavelengths will come out at different angles as you send it through that diffraction grating. So I've got my diffraction grating here. I got my phone, and I'll go ahead and hold the diffraction grating up over the webcam. And you see how off to the side there we have these different colors? I'm going to, at this point, turn off the background behind me to make sure that there's no interference with that zoom background and what I'm trying to show you here. And so here we go. You see all the colors of the rainbow there, including the green. I think Zoom had previously knocked out the green to put it with the background. And I actually see the two different series of the rainbow. Real close to the bright light, I see one that is a little bit smaller, and then if I look out further away, it is stretched out a little more. But all the colors are there in that white light of the rainbow. If you do something similar, use a diffraction grating to look at light from the sun, not from your phone, and you spread it out, this is what you see. You do see all the colors of the rainbow with some specific exceptions. These are called absorption lines. You kind of read this like a book. We're going from the shortest wavelength light at the upper left here. You go across the line, you go down to the next line, keep going, going till the end. Here we be getting into the longest wavelength light. And notice that there are specific wavelengths that are missing, specific colors that are missing. Those are going to be clues about what is in the atmosphere that's absorbing that light, what is in the sun's atmosphere absorbing that light. Where those lines occur give us information about not only what is in the sun, but how hot it is in the sun, and so on. There's going to be a lot of information embedded in these spectra. I have set up over on the side here some spectral tubes. And what these are tubes of various gases. Like here, this particular one on the left, that's hydrogen. And I'm going to run some electricity through that tube right there. And if you want to start to appreciate what's happening, you can think about the fact that the electrons on that hydrogen are getting knocked up by the electricity that's running through there. And then the electrons are going to fall back down onto the atom. And as they do, they're going to emit light of specific wavelengths. So if I hold the diffraction grating over top, you can see on my shoulder right here, you see that red line? We are, with the help of the diffraction grating, sending the different wavelengths in different directions. I think I see a second line, and I don't have my video pinned. It's small on my screen. Do you see 2 lines or 3 lines? How many lines do you see? Somebody sees 2. If I had a darker room, you know, without all the sunlight and stuff around, maybe set it up a little better, you can often see a 3rd line. What if we go and we look at some other kind of element, like I have over here, helium, the second most abundant element in the universe, right? And I look at its spectral lines, right away I can see they're different. I see a red one, I see a yellow one, I see a green one. You see that there? Somebody in the chat is saying now they see 3 lines. Yeah. I see at least 3. I see 3. Now we can, to make the point, go ahead and put these 2 tubes on top of one another. And, you know, this way, as we look at it through the diffraction grating, you can see that the 2 sequence or patterns of lines are different. The hydrogen's on the top, the helium's on the bottom. You can see offset from that these spectral lines, and they don't follow the same pattern. So if you're looking at some celestial object and you see the pattern on the top, then you're spotting hydrogen. If you see the pattern on the bottom, you're spotting helium. And if you see some combination, then you're spotting a combination of the 2. Now, some of you saw 4 lines when you looked closely. I'm going to turn on the spectral tube for neon. And you tell me, nice orange color, you tell me how many lines you see with neon. There's a whole slew of them. Many of them are in the orange there, and that's why overall this thing looks orange, right? But, you know, if you look at neon signs, nowadays a quote-unquote neon sign no longer necessarily has neon as the gas inside of it, but a traditional neon sign would be just kind of like this. You send electricity through neon, it excites the electrons come back down, they emit light. Okay, so as we've seen, each kind of atom has its own unique spectral fingerprint. We saw that there for the hydrogen, for the helium, for the neon. This image in the center here shows us helium's spectrum. Remember that red line, that yellow line, the green line, and some of these other lines were harder to make out in the demonstration, but they were there. You might have actually caught a glimpse of some of them. I think if you looked carefully, you could see the bluish line there. Now, sodium has some orange lines. Neon, we saw, had a lot of orange and reddish lines. And so in astronomy, if you ever identify this pattern of lines or some combination of these patterns, then you can start to learn information about the composition of the celestial object you're looking at. Not only that, as we'll eventually discuss, you can learn about the temperatures in this object. Right now, we're just saying that these spectral lines exist. Soon enough, we'll start to understand why they exist. And it'll have to do with electrons populating different energy levels within the states of an atom or molecule and transitioning among those states. And so if the electrons are populating a certain initial state, well, then it could transition out of that. But if it's, say, too hot to populate an initial state or too cold for it to populate an initial state, there would be no transition away from that initial state. So we're going to also be able to learn things about temperature of the material that's emitting this light. Now, down at the bottom, we get that idea that there could be multiple atoms and molecules that are contributing. In stars, they're usually hot enough that you just have atoms on the surface, but you could imagine looking at the spectra of atmospheres of planets, for example. And we'll be talking about also not just emission lines, but absorption lines that those planets' atmospheres could give. And so down in the bottom example, we see that there's lines due to helium, there's lines due to oxygen, lines due to neon. A single plus means that it's been singly ionized. One electron has been ripped off. So overall, it has a positive charge of 1 E, where E is the charge of a proton. And doubly ionized neon would be written as Ne++. Now, there are 3 main types of spectra. We were talking about the emission spectrum. And if you look carefully down at the bottom of this graph here, you see how there's like a few purples. They've drawn them as purple, even though it's in the ultraviolet, because what better color could you choose? Where it gets dark, but then it's bright, and then it's dark, and then it's bright. You see this band of colors across the bottom is indicative of what you would have on your spectrometer at the back end of a telescope. Your light comes through the telescope, it hits a prism or a diffraction grating and spreads out. And then the blue colors are off here on the left, the reddish colors, that is the longer wavelength on the right. And we can convert this image into a spectrum graph with intensity on the vertical axis and wavelength on the horizontal axis. And so here, wherever there's a bright line, you would see a bump upwards in the intensity. The smoothly varying regions we would call the continuum or the continuous spectrum. And then if there's ever some dips downward at specific wavelengths, that is at specific colors, if you will, then we would call those absorption lines. And so the basic idea is that if you were looking at a spectral tube like we were a few moments ago, you would get emission features. But imagine you had a bright light source and some cool gas between you and that bright light source. Well, the bright light source could shine light, which then gets absorbed and scattered off in different directions at specific wavelengths. And so specific wavelengths don't make it to you, the observer, because of this cool gas in front of the light source. And so if it were something like that, you might see absorption lines rather than emission lines. Now in section 5.2, we talk about the fact that light has this duality. And in fact, as we'll later learn, it's not just light, but all matter, which as well has this duality. Einstein first realized this particle nature of light, right? The other part of the duality is the wave-like nature. And it's pretty clear that light behaves like a wave. I mean, it bends around corners. When it passes a corner, it has a little bit of a bend. We saw the Young's double slit experiment demonstrated to us earlier. And so, yeah, it behaves like a wave. But what Einstein realized is that it doesn't behave only like a wave with this photoelectric effect. So if you shine light at a metal, then you can, from that light, knock electrons off. And what Einstein realized is that you had to have the frequency of the light be high enough above some critical threshold before the electrons would get ejected. If you had very low frequency light that you were shining on it, even if you made it super bright, right? So you have, some radio waves that are really low frequency, very small numbers for their frequency, then they're not going to be able to knock off the electrons, even if you shine as much as you can at them. And in contrast, if you want to knock the electrons off, shine short wavelength light at it, high frequency light. And even then, you don't need to have a lot. Like if you just send one X-ray photon towards it, then man, you pop off an electron. So the idea here is that you can understand, you can appreciate that it's not just the total amount of energy per time, say, that you're sending at the metal that decides how many electrons get knocked off. It's how much each individual particle of light. This is how you can understand this photoelectric effect, that there are particles of light, and those particles of light, if each one is energetic enough, can knock off an electron. And so if you have a high enough energy photon, it can knock off an electron. If that photon, that particle of light, doesn't have enough energy, it cannot knock off the electron. You could send a lot of low energy photons, nothing gets knocked off because each individual photon is not energetic enough to knock the electron off. You can kind of think about photons as the quantization of light. So now a photon has an energy E equals h times nu, where h is Planck's constant. We introduced this earlier. Nu is the frequency. And remember, nu times lambda is the speed of light. The wavelength lambda multiplied by the frequency nu, well, that's length times 1 over time. Yep, that's going to be a length per time. That's going to be the speed at which the wave goes by. If you have lambda representing the length per cycle and nu representing the number of cycles per time, well, length per cycle times number of cycles per time is the length per time that the wave is covering. And so here you can solve that for nu equals c over lambda. And so if you want to know the energy of a photon in terms of lambda, it's hc over lambda. Now, photons also carry momentum p with them. Here we have E equals pc. The p we see is just h over lambda. As we'll be discussing in more detail, Planck's constant h is an angular momentum. So if you divide it by a wavelength, you do get this momentum p. So when you're out laying on the beach and you're being bombarded by the waves from our sun, the photons from our sun, they are carrying energy and momentum, and they hit you and they actually transfer energy, and they also apply a momentum transfer to you. There's a pressure from that light being absorbed by your skin. Okay, in section 5.3, we discussed the Bohr model of the atom. So I'm going to stop sharing screen right now so that we can go to the board behind me and start to talk about the Bohr model of, in general, hydrogenic atoms. What do we mean by hydrogenic? Hydrogen-like. Hydrogen has one proton in its center, and it's orbited by one electron. And you could imagine other hydrogen-like atoms. Helium, for example, if it has one electron going around it, we could call it hydrogenic. Because, yeah, the nucleus is different. There's 2 protons and 2 neutrons, but there's still just one electron orbiting that charged nucleus. So in that sense, it's very much like a hydrogen atom. It's just that the strength of the Coulomb force between the nucleus and the electron is going to be different because there's 2 protons rather than 1. And the reduced mass would be a little different because there's 4 nucleons instead of just 1. And deuterium, tritium, the different isotopes of hydrogen, they're hydrogenic as well. Deuterium, remember, is a proton and a neutron, and it would have a different mean molecular weight, the electron and the nucleus, if you're considering that it would have a different reduced mass, I should say, mu, because you have the electron and the nucleus, which is now a proton and a neutron instead of just a proton. And a tritium, you have a proton and 2 neutrons, and 1 electron, still hydrogenic. Helium-3, proton, 2 neutrons, and a single electron. That's a hydrogenic atom. Whenever you have a nucleus orbited by 1 electron, that will be what we call a hydrogenic atom. So I'm going to let Z be the atomic number. It's the number of protons in my nucleus. So Z is what we use when we're ordering the elements on the periodic table. The first element on the periodic table is, of course, hydrogen. Z equal 1. It's got 1 proton, regardless of whether it has more than 1 neutron or not. The next element on the periodic table, Z equal to 2, is helium, and so on and so forth. Now, in the nucleus, we have protons and neutrons. Their masses are about equal to one another. You can look up in the inside front cover of your textbook how they differ slightly, but they're about equal to one another. And they are about 1,800 times as massive as an electron. And so it's worth noting that the proton and the neutron are each very much more massive than what an electron is. So Bohr's model is this semi-classical model for describing these atoms. And we now know, of course, that quantum mechanics does a better job where you think about electron clouds around atoms. But in the Bohr model, which was the first model that successfully predicted and explained the qualitative behavior of atoms, you just have an electron actually orbiting around. And in that sense, it's semi-classical. Why semi-classical, not fully classical if it's doing orbiting? Well, it's only going to be allowed to orbit at specific radii. The radii for which, if you treat the electron like a wave, the wave does not interfere with itself. So we'll introduce in more detail in the next class the de Broglie wavelength. And the de Broglie wavelength of the electron tells you, it's a way of thinking about matter, an electron, like a wave. And if the electron makes an orbit and you've gone through an integer number of wavelengths by the time it gets around, it would not destructively interfere with itself. But if you try to orbit at one of these disallowed radii, then you come around and maybe the wave is out of phase with itself where it was an orbit ago. And so it cancels out. And so this was the idea that allowed de Broglie and Bohr, Bohr built on this de Broglie wavelength idea to pick out the specific radii at which the electron could orbit. So because the electron can only orbit at these specific radii, things are quantized. In particular, the angular momentum that the electron can have is going to be quantized. There are only discrete values that it can take. And so I will write down what those values are. The angular momentum L, which in the semi-classical model is the reduced mass multiplied by the speed multiplied by the radius. So here's the nucleus, here's the electron orbiting around at some radius r and some speed v in this particular model. And what we're saying is that it's quantized with n being an integer as n times h over 2 pi. Now, if you like, you can write this as n times h bar. H bar is known as the reduced Planck constant. And you can tell from that last equal sign that it is equal to h over 2 pi. And so we've written down earlier in the course what h is. Simply divide it by 2 pi, and you now know what h bar is as well. And so this is equation 5.12 that we're talking about here, this angular momentum quantization equation. So you should commit to memory that h bar, and therefore h, is an angular momentum. You should know what the dimensions of h bar are. And you can see that from this equation right here. L is some integer number n of h bars. The angular momentum can be 1 or 2 or 3, for example, right? But it cannot be pi times h bar or 1.5 times h bar. Now, what I'd like to be able to do is say, okay, well, if there are only specific angular momenta that are allowed, that's going to mean there's only specific radii that this can orbit at. And so I want to now determine what those allowed radii are. You see, the speed v is just going to be achievable from r and knowledge of what the force is at that r. And the force is going to be due to the Coulomb attraction between the proton, or the nucleus more generally, and the electron. So, okay, the classical equation that describes motion is F equals ma. So that's going to be our starting point, right? We said this was a semi-classical description. The semi part comes from the fact that things are quantized, and the classical part comes from the fact that we're going to be using F equals ma, not Schrodinger's equation. So F net is equal to the reduced mass times the acceleration. We worked hard on the last homework set number 3, to convince ourselves that you could treat a two-body problem with a mu in it. And here we're going to make use of that, right? The force in that set number 3 problem was gravity, but the force here is the attraction. So there's the charge of the nucleus, Z times E. There's the charge of the electron in magnitude E. And then there's the distance between them squared. And if I just multiply this by K, I get a force. Here K is, as you might learn in an introductory electromagnetism course, it's 1 over 4 pi epsilon naught. It's the electromagnetic analog of capital G in gravity, right? It's this constant that you multiply the product of the charges by to get a force. So the numerical value is 9 times 10 to the 9 in SI units. That is Newton meter squared per Coulomb squared. And notice that has to be the right units for SI, because there's a charge times a charge. That would kill off this Coulomb squared there. We're dividing by a meter squared here, dimensionally or unit wise. So that would kill off this meter squared there, and we'd just be left with newtons. That is then indeed a force on the left-hand side here. So K, Q1, Q2 over R squared. The minus sign is because, well, one's positive and one's negative. And so you can think about the minus sign as being associated with the electron. But also, if you think about this directionally, the electron is pulled in toward the proton in the way that it accelerates. And so the minus sign is to smaller values of R. I'm going to drop the vector signs from the left and the right-hand side here, because positive would be in the positive R direction, negative would be in the decreasing, I guess, R direction. So this equals mass, which in this case is the reduced mass. Maybe it's worth pointing out on the side over here what mu is. Mu is equal to the mass of the nucleus times the mass of the electron divided by the mass of the nucleus plus the mass of the electron. Right, so to a very good approximation, this is going to be equal to the mass of the electron. Because remember, ME is a lot less than MM. It's 1,800 times less than MN. Oh, here I should maybe write nuke instead of N, because I already used M sub N to mean the mass of a neutron. And so I should be careful here. It's the mass of the nucleus that I'm referring to at this point. And so there we go. Still, the mass of an electron is going to be much, much less than the mass of a nucleus. So you can think about neglecting this in many cases, depending on how accurate you want to be. And then M nuke over M nuke makes a ratio of 1. And so Yeah, the reduced mass is about roughly the mass of the electron, pretty darn close. All right, so there's our mu, and then the acceleration is from centripetal acceleration, negative v squared over r. And centripetal acceleration, as the name implies, pedal means towards the center, centripetal is towards the center, is negative v squared over r. So we have a condition here, I'll call this equation star. And then what I'm going to do is I'm going to use the velocity that I got from discretizing the angular momentum in for the velocity v on the right-hand side here. And let's go ahead and then see what we get. First of all, I'll cancel the minus signs that are on both sides. And so I have positive k z e squared over r squared is equal to mu over r. And now the only thing I haven't accounted for yet is this v squared. And so let me come back up here, and this is what I'm going to be using. I'll write it in a different color so that it maybe stands out a little better. What I'm going to be using is that v is equal to n h bar over mu times r. See, I just solved for v up here. And so this is going to be n h bar over mu times r, the quantity squared. All right, well, at this point, there's a bunch of r's floating around. And it's r that I'm trying to get. I'm trying to figure out at what radii does the electron orbit, what radii is it allowed to be orbiting. And so let me go ahead and solve for that particular r. I'll note that I have an r squared in the denominator there, and that can cancel with this r in the denominator because it's also squared. And now I'll take this r in the denominator on the right, bring it up to the numerator on the left, and everything else is going to go to the right-hand side. So all this stuff in the numerator on the left is going to go to the denominator on the right. And so once we've done that, we get that r is equal to n squared h bar squared divided by kz e squared, and then a single power of mu in the denominator, because we had one mu in the numerator, we had this mu in the denominator, but it was squared. So overall, we're just left with a single power of mu in the denominator. And so, okay, fine. I mean, it's pretty cool, but why don't we write this as A naught, where A naught is what's going to be called the Bohr radius, n squared multiplied by m sub e over z times mu. Now, the reason for that is because this quantity here that I am about to encircle, that is approximately equal to 1 for hydrogen, and more generally 1 over z. So this is about equal to 1 for hydrogen. Why? Well, we got done saying here a moment ago that mu is pretty darn close to me. So me over mu, that's always going to be very close to 1. And if it's hydrogen, well, at least the, hydrogen, then z is equal to 1. And so the whole thing is equal to 1. So if you're just dealing with hydrogen and you're not worried about hydrogenic atoms, you don't care about singly ionized helium, etc., then you can just drop that term altogether and just write this as r is A naught n squared. But if you want to be precise and more general, then you could keep that term in it. Now you might say, where did this me come from? Well, it came from what our definition of A naught is. I'm going to have an m sub e inside of the definition of this Bohr radius A naught. So let me write out what A naught is. The Bohr radius A naught is defined to be h bar squared over k e squared times m sub e. I'm sorry, it's going to be divided by m sub e. And you see, these are all just constants. H bar, k, charge of an electron, e, mass of an electron. So that just has a value. This turns out to be 0.529 angstroms. Remember, an angstrom is 10 to the minus 10 meters, or 1/10 of a nanometer. And so because that ME is down in the denominator in the definition of A naught, imagine plugging in for that right-hand side in for A naught right there. You'd get that ME in the denominator to cancel with that ME in the numerator. So that's why it all balanced out like that. So, okay, we now know what radii are allowed for the electron to orbit in this model. Note that it scales like n squared. So the innermost allowable orbit is going to be for n equal to 1. That's going to be called the ground state. It has a certain radius that it orbits at. For hydrogen, it orbits at the Bohr radius. So we've just kind of derived, if you will, a measure of the size of an atom. We're saying the size of a ground state hydrogen atom is a sphere with 0.5 angstroms as the radius. So in other words, it's going to be about 1 angstrom across. And in fact, that's why this whole angstrom unit exists at all. It's because it's a very convenient unit to be able to measure sizes of atoms in. If you go to the next orbit out, well, that's n equal to 2. 2 squared is 4. So that's going to be 4 times the Bohr radius where the electron is allowed to orbit. The next radius out is 3 squared, or 9 times the Bohr radius, et cetera, et cetera. Note the n squared right there. Okay, well, what I'd like to do next is to get the velocities and energies in terms of n alone. We have expressions for the velocity, right? We use this one, for example, it's n h bar over mu r, but it has this n in it. But now that we know how r depends on n, we could get v in terms of n alone. So let me go ahead and erase the board, and then we'll do that. All right, so we're now going to get the velocity of the electron as it orbits in the atom in terms of n alone, the integer that quantifies which state we are in. And then once we have the velocity, from that we can get the kinetic energy. We'll also, for n, know what the potential energy due to the attraction between the nucleus and the electron is. And so we could get the total energy of the system. So let's start by getting that radius in terms of n. We did that. Now we're going to get velocity in terms of just n. We're going to be plugging in for that radius right there. So this is n h bar over mu times 1 over r. So what I had for r, I'm going to have to flip. I get k z e squared mu, all divided by n squared h bar squared. So the mu's make a ratio of 1. I've got NH bar here. I've got 2 powers of NH bar in the denominator. So if I simplify, I get k z e squared over NH bar. So this result here makes sense. If you think about the fact that as you go to larger values of n, you're getting farther out. Well, just think about what it's like with planets orbiting a star. They go slower as you're farther out. So larger n values give you smaller velocities. Also, if you had z greater than 1, maybe it's helium in the center, so you have 2 protons, there's going to be a stronger attraction of that electron in towards the center. And so in order to maintain an orbit at a particular location, it's going to have a larger speed than it would have if z were only equal to 1. And so we're not surprised to see z up in the numerator there. just like if you had a more massive star, you'd need at a particular distance away a larger speed to maintain a circular orbit. So now that we know V, we can, as a function of n, get the kinetic energy in the system. And I'm going to go ahead and use the reduced mass mu. 1/2 mu V squared is equal to 1/2 mu multiplied by, and now K times Z E squared over NH bar. That's what V is, and that gets squared. So we're just using that last expression we had just found for V in our new expression for kinetic energy. And I'll leave it written like that. This is the kinetic energy that we just calculated. Now let's think about the potential energy. And remember, the potential energy for gravity is minus gm1m2 over r. And when you take minus the derivative of a potential energy, you get a force. Well, the force in electrostatics is kq1q2 over r squared. Just like gravity, it's gm1m2 over r squared with a minus sign up front. And so both of them are 1 over r squared forces. So you won't be surprised to learn, and in fact, you probably already did learn in your introductory E&M course, that the potential energy associated with 2 point charges interacting is kq1, q2 over r. So we'll make use of that here. I'll call the potential energy U. This is K times Q1, which is the charge of the nucleus, times Q2, which is negative E, so I'll bring the minus sign out front. That's the charge of the electron, over R. And so this is minus KZE squared times 1 over R. I've got my expression for R there, so let me flip it. It's KZE squared mu, all divided by n squared h bar squared. And so let me now simplify this. I have 1 power of mu, which I'll bring out front. It's a potential energy of a bound orbit, so not surprisingly, it's negative. I'll leave that out front. And as for the rest, I've got 2 powers of K, 2 powers of Z, 4 powers of E, 2 powers of N in the denominator, 2 powers of H bar in the denominator. So I always have an even number of power. So I'll just write this as KZ E squared over N H bar, that whole quantity squared. Now, if you look back at what we had just got for kinetic energy, you'll see that the 2 expressions are very similar to one another. That's perhaps not surprising given the virial theorem that we know about, that the kinetic energy is minus half of the potential energy when you have a 1 over r squared force like gravity, or like in this case, the Coulomb force. And so, yeah, not surprisingly, they have the same form, just a different numerical coefficient out front. The total energy is going to be the sum of these 2 energies. E is equal to K plus U. This K is kinetic energy, which is 1/2 of U from what we've noticed, because after all, this guy up here is just minus 1/2 of U. And so for K, you could imagine putting in minus 1/2 U plus U gets you to 1/2 of a U. And so overall, this is minus mu over 2 of the quantity KZ E squared over NH bar all squared. All right, so fine. Why don't we go ahead and write out what this is in terms of electron volts. This is equal to minus 13.6 electron volts per n squared multiplied by z squared for mu equal to the mass of an electron, at least, which it very nearly is. And so there you go. For hydrogen, where Z equals 1, we now know what the electron energy levels are. The n equal to 1 state is minus 13.6 eV, n equal to 2 state is 1/4 that, and so on. For singly ionized helium, we'd have to put in Z equal to 2 here because there are 2 protons in a helium nucleus. So all the energies would be 4 times bigger, that is 4 times further away from 0 in that particular case. And it's a good thing to remember that radii scale like 1/Z and that energy scale like Z squared. I've seen that question pop up on an example and actual GRE physics type questions in the past. And it's kind of easy enough to understand why this scales like Z squared. First of all, we already talked about how R varies inversely with Z. If you have a large, well, maybe we didn't talk about it, I don't remember, but here's why. If you have a bigger charge in your nucleus, that's going to draw the electron in closer. And so, not surprisingly, as Z gets bigger, everything gets tucked in closer to the nucleus because there's that stronger force. And so we're not surprised to see a 1/Z here. But now, when R's are all smaller, you get the energies to be smaller as well. And so if you look at things like the potential energy, you've got 1 power of Z that comes from the fact that the charge itself of the nucleus is more, and another power of Z because you've tucked things in closer. R is proportional to 1/Z, so you get 2 powers of Z in the end for the energy. So these are then the energy levels for the hydrogenic atom. I'm going to go back now to the PowerPoint slides so that we can think about what this means in a more graphical way. Here, I'm looking at the energy levels for hydrogen. Notice that over on the left side, we've labeled the states from n equal 1 up to infinity. So n equal to 1, it's the same n we were talking about on the board, the so-called ground state, and it has an energy associated with it of minus 13.6 eV. We just derived, in a sense, that minus 13.6 eV. It came from a combination of the charge of a proton and the reduced Planck constant and so forth. And now if you take 13.6 and divide it by 4, well, you divide by 2, you get 6.8, divide by 2 again, you get minus 3.4. So indeed, the n equal to 2 state is minus 3.4 eV. And if you take 13.6 and you divide by 9, you get the energy of the n equal to 3 state. In general, if you take minus 13.6 eV and divide by n squared, you get the energy of the nth state. And so you can see that the energy levels get spaced closer and closer and closer together. And n can be any integer in principle all the way up to infinity. And if you were to divide by n squared where n approaches infinity, well, you're dividing by a really large number, infinity in that limit, and so you would get 0. Electrons can exist at higher energies than that, but they wouldn't be bound to the nucleus any longer. They would be free electrons. You would have ionized that atom. So the idea is that electrons can exist at these energy levels and it can jump between them. It could, for example, jump from state 2 down to state 1. That would be called a Lyman alpha transition. You want to guess what Lyman beta is? From 3 to 1. Lyman gamma, 4 to 1, et cetera, et cetera. Because alpha, beta, gamma, delta, those are the letters of the Greek alphabet in order. And so a Lyman alpha photon is quite energetic. It's 10.2 eV. If you take that energy, and remember E is equal to H times nu, or it's equal to HC over lambda, you can get a frequency or a wavelength associated with it. And if you calculate that wavelength, you'll find that it is shorter than what the human eye can see. It's in the ultraviolet. In fact, all of the Lyman series photons that would be emitted are in the ultraviolet. You see, why am I talking about photons? Well, When the electron drops from, say, 2 to 1, it loses energy, and that energy goes into a photon being emitted. Perhaps that's not too surprising, because after all, you're changing the electric field by changing the state of this electron. And so you make a perturbation in the electric field that propagates outward, that materializes, it manifests itself as a photon of light. So all of these Lyman series photons that you would get from an electron transitioning from a high state down to 1, they're all in the ultraviolet. If you go to the Balmer series, that means that the electron ends at n equal to 2. And the first 4 of those, or 3, depending on the biology of your eye, are going to be visible to you. So if you go from 3 to 2, that's going to be a red line. You work it out, like figure out what the energy difference is here. You know, subtract these two numbers from one another. What's the difference between 1.51 and 3.4 eV? That tells you how much energy has gone into the photon. Set that equal to hc over lambda and solve for lambda. You get 656 nanometers. That's the red line we saw in the spectral tubes when we looked at hydrogen. If instead the transition is from 4 to 2, there you kind of have that teal green / cyan type color, right? That works out to be 486 nanometers. Look, there's a larger energy jump, so there's more energy in the photon. That's shorter wavelength. If it's 5 to 2, right, that's the Balmer gamma photon. That would be 434 nanometers. And that's just at the boundary of what most people can see. Under idealized conditions, and if your eyes are good, you might be able to see the delta photon from the Balmer series, where we go from 6 down to 2. That gives you 410 nanometer wavelength light. But that's tricky. I myself haven't seen that before. It's a little bit outside the range of what my eyes can detect. Now, if you go to the Passion and the Bracket and the other series, you're going to have infrared photons, because the energy jumps of anything that ends in state 3 or higher are not going to be energetic enough to give you a visible photon. And so you will at best get an infrared radiation photon that we're talking about here. So 4 to 2, 5, or 4 to 3, 5 to 3, 6 to 3, etc. They're all in the Passion series. They're all going to give you infrared photons. Now, it's worth pointing out, because of quantum mechanical effects that you've studied in other courses or will study in quantum mechanics, that you can populate these states with more than one electron. So for example, in the ground state, you can have a spin up and a spin down electron. And so it's not that you can only have one electron in these states, but there's a fixed number of electrons with a well-defined pattern that you can populate in each of those principal states. So it's worth emphasizing that there are now going to be discrete wavelengths of light that could be emitted by an atom or absorbed by an atom. If the electron is going from a higher state to a lower state, that's where you have emission of light. But for the absorption of light, you have the electron going from the lower state to a higher state. So maybe your electron is just hanging out in the ground state of hydrogen. A photon with 10.2 eV comes along and hits it. Why 10.2 eV? Remember, that's the difference in energy levels between n equal 1 and n equal to 2. That's just the right amount of energy to absorb the photon and knock the electron up to n equal 2. And so that would be like this, this third arrow shown here. These first two arrows are transitions that cannot happen, right? If a 5 eV photon comes along, it'll just pass right on by that electron in the ground state, because it's not the right energy to knock it up to one of the allowable states. Or if a photon with 11 eV comes by, then it'll knock it up. It wouldn't be able to knock it up because there's no state between 2 and 3 to put it to. And so you need just the right amount of energy. There is a little bit of wiggle room depending on the lifetime of the states, but basically you need 10.2 eV photon to come by to knock that electron up. Now, that electron, once knocked up to n equal to 2, may eventually will, under normal circumstances, fall back down to n equal to 1 if it's not excited again. And then it would release a photon of 10.2 eV. So in a sense, you would have had a 10.2 eV photon come along, it's absorbed, you knock the electron up, electron falls back down. And now this new 10.2 eV photon could go off in some new direction. And so if you're over there observing, although the 10.2 eV photon that came along at the beginning was headed your way, it gets scattered off in some other direction, and you would see an absorption at that particular wavelength. Not one of the ones shown here, because I was talking about an ultraviolet photon at 10.2 eV, but you could imagine that a photon comes along and knocks something up from level 2 to level 3, for example, and that would give you the absorption line at 656 nanometers. Now, if a photon with enough energy comes along, let's say more than 10.2 eV, it could knock something in the n equal 2 state off the atom altogether. And that's what this arrow is representing. Or even if the electron were down in the ground state, if a photon of at least 13.6 eV comes along, it can knock the electron off of the atom altogether. I want to finish by just doing a fairly, I hope, straightforward example problem to allow us to think about what we've been learning. And then next time what we'll be doing is we'll talk more about de Broglie wavelengths and how light and matter both share this duality. But let me erase the board and do an example problem here. All right, here we go. Here's our example. We want to find the radius r and energy E for the ground state of singly ionized helium, helium-4, say. And so the way we write singly ionized helium is He Roman numeral 2. In general, the way an astronomer would talk about a neutral element would be to use a Roman numeral 1. So H Roman numeral 1, H1 is neutral hydrogen, for example. He1 is neutral helium. He2 means, well, you've stripped one electron off. So if we're talking about He2, what you have is your nucleus being orbited by a single electron. Because remember, the nucleus has 2 protons in it. If there's 1 electron instead of 2, it's singly ionized. And so, okay, we said there were 2 protons in a helium nucleus. And so Z is equal to 2. It's the second element on the periodic table. Now, what about N? You know what N is? It's 1, because we're talking about the ground state. That's the lowest energy state, the most negative. And so we want to know the radius associated with that ground state. And we found that it's A0 N squared over Z in class today. And so I'll plug in N equal to 1 and Z equal to 2, and I get half of A0. So that's 0.265 angstroms. And even though we're doing this semi-classically, and we know in quantum mechanics that you talk about electron clouds, this gives you the length scale over which the probability distribution function that describes such an electron would be located. And now if we want to know the energy level associated with that ground state, it's minus 13.6 eV multiplied by, well, Z squared over 1. Over 1 because, well, it's over 1 squared because we have N equal to 1, but it's Z squared or 2 squared in the numerator. So this is 4 times minus 13.6 or minus 54.4 eV. It makes sense that compared to hydrogen, that this electron should be tucked in closer in the ground state. For hydrogen, it's out at twice this distance the ground state electron is. But now that you have more positive charge in the nucleus, 2 instead of 1 protons, it tucks in closer. And when it's in closer, you get more negative energy as a result. Because in the KQQ over R, which describes the potential energy that you would have, you've got one of the Q's which is twice as large as it was in hydrogen, and plus the R is twice as small, and so overall you get 4 times the energy of what you would have had in the ground state of hydrogen. Same question now, but for the third element on the periodic table, lithium. It's the third element, so what is Z? That's right, Z is 3. We're still interested in the ground state, so still N equal to 1. Now, if we want to know what R1 is, well, it's A naught times N squared over 3. N squared is 1, Z is now 3, so it's A naught over 3. It's 0.176 angstroms. Now, I should point out that I'm talking here about doubly ionized lithium. It's more complicated if it weren't doubly ionized, because you don't have just a single electron going around, and so you have to worry about things like electron shielding and so on. And we're not doing that. That's not a hydrogenic atom. So we made it doubly ionized so that we could work this particular problem. And notice that it's Roman numeral 3 on the lithium. Lithium 1 would be neutral lithium. Lithium 2, you've ripped off one of the 3 electrons, so there would be 2 electrons remaining at singly ionized. And lithium 3, you've ripped off 2 electrons of the 3, so there's only 1 remaining. And that's what we need to have a hydrogenic atom. We need to have just 1 electron. So sure, there are 3 protons in the nucleus, but for it to be hydrogenic, there can only be this 1 electron that is orbiting around. And then finally, the energy associated with this ground state of doubly ionized lithium is 13.6 eV times Z squared over N squared, but N is 1. So it's 9 times that negative 13.6 eV. So this is negative 122 eV. Not surprisingly, it's even more negative than what we had in the singly ionized helium case, because the electron's even closer to the nucleus, and the nucleus has more charge than before. And so the combination of those two things each give you a factor of 3 if you were comparing all the way back to hydrogen, and the 3 squared, or 9 times what you had in hydrogen, is the answer for the ground state energy here. Okay, that's all that we are going to cover for today. I will see you next time. Bye-bye.